Welcome to this lecture on AC system classification based on the deployed refrigeration cycle. The task of absorbing heat from the space to be air conditioned, then rejecting it to the surroundings, is done by a substance called refrigerant. In order to perform this task on a continuing basis, the refrigerant perpetually executes a cycle called refrigeration cycle. During each cycle, the refrigerant changes phase from liquid to vapor, known as evaporation or boiling, and then back from vapor to liquid, known as condensation. Heat absorption takes place during evaporation, that is boiling, while heat rejection takes place during condensation. In this lecture, we give you an overview of two types of refrigeration cycle, namely vapor compression cycle and vapor absorption cycle. We now begin our study of the vapor compression cycle. In this slide, the components of a simple air conditioning system implementing the vapor compression cycle are shown. The key components are the compressor, the condenser, the thermal expansion valve, and the evaporator. This slide shows these key components and their interconnection. In each refrigeration cycle, the refrigerant flows from the compressor to the condenser, then through the expansion device to the evaporator and back to the compressor. Low pressure, low temperature liquid refrigerant enters the evaporator. The refrigerant absorbs heat from the air conditioned space and gets transformed to low pressure, low temperature vapor. Thereafter, the compressor raises the pressure and temperature of the vapor. The refrigerant vapor now flows through the condenser, where it rejects its heat to the ambient air or to water, as the case may be, and gets transformed to high pressure, high temperature liquid. The refrigerant finally flows through the expansion device, where it gets transformed back to low pressure, low temperature liquid. This slide is intended to give you an idea of the orders of magnitude of the temperatures and pressures encountered in the refrigeration cycle of an air conditioning system. The schematic is perhaps of a simple 1-ton R22 refrigerant based room air conditioner, which is maintaining the room air at 75 degrees Fahrenheit, 50 degrees relative humidity, while the outside ambient air is at 95 degrees Fahrenheit. You will find the boiling points of R22 as well as of a few other popular refrigerants at different vapor pressures in table 5.1 of ISHRAE Databook 2017. Notice that the R22 entering the evaporator is 75% liquid and 25% saturated vapor at 40 degrees Fahrenheit and 68.6 psig vapor pressure. Now, why is it 75% liquid and not 100% liquid while at the inlet of the expansion device, it is 100% liquid. The reason is that when the refrigerant passes through the expansion device, its pressure falls steeply from 278.1 psig to 68.6 psig, and it keeps boiling, absorbing latent heat from the liquid and lowering its temperature all the way down to 40 degrees Fahrenheit, which is the temperature at which its saturation vapor pressure is 68.6 psig. You are encouraged to verify this by referring to table 1.5 of ISHRAE Data Book 2017. Now back to the evaporator. As the liquid vapor mixture flows through the evaporator, it absorbs heat from the inside air, which is at a higher temperature of 75 degrees Fahrenheit, until it becomes 100% vapor. Indeed, by the time it reaches the compressor inlet, it is 100% slightly superheated vapor at about 60 degrees Fahrenheit. By the time the R22 vapor leaves the compressor, its pressure has been raised to 278.1 psig and temperature to 200 degrees Fahrenheit. The vapor now enters the condenser and begins its flow through it. And as it flows, it rejects heat to the outside air, which is at a lower temperature of 95 degrees Fahrenheit. Somewhere midway in the condenser, the vapor's temperature is down to 125 degrees Fahrenheit, whereupon it begins condensing into liquid. By the time it finishes its journey through the condenser, it has fully changed phase to liquid. And when it reaches the expansion device inlet, it is a 100% subcooled liquid at about 105 degrees Fahrenheit. We hope you now have a clear idea of how the vapor compression cycle enables absorbing heat from the air conditioned space and rejecting the same into the outside air. We will now describe the vapor absorption cycle and specifically show you in what way it differs from the vapor compression cycle. In this slide is shown the schematic diagram of the vapor absorption cycle. It will be seen that it is identical to the vapor compression cycle, except that the mechanical compressor is replaced by a thermal compressor. The vapor absorption cycle involves two fluids, namely refrigerant and absorbent. The refrigerant plays the same role as in the vapor compression cycle, namely absorb heat in the evaporator and reject heat in the condenser. A typical refrigerant absorbent combination is ammonia and water. The thermal compressor comprises three components, namely absorber, pump and generator. The absorber absorbs refrigerant vapor coming from the evaporator to form a strong solution, that is a rich solution of the refrigerant in the absorbent. For example, of the refrigerant ammonia in the absorbent water. Next, the pump pumps this rich solution from the absorber into the generator. The generator distills the refrigerant vapor from out of the rich solution using an external heat source. The vapor now moves on to the condenser. The lean or weak solution which is left behind is recycled to the absorber. The benefits of the vapor absorption cycle are: the power required to pump the rich solution is much less than that required by the compressor in the vapor compression cycle. The heat source used for distillation in the generator can be a cheap source, for example, waste heat of some other process. The drawbacks are low coefficient of performance, large equipment sizes, and difficulty of operating and maintaining vapor absorption systems. We end this lecture by noting that the vast majority of air conditioning systems deploy the vapor compression cycle. In the next lecture, we classify air conditioning systems based on the cooling medium used to cool the indoor air. Thanks for watching.